Okay, in this short video, what I'm going to do is I'm actually going to combine a lot of what we have thus far talked about in class with respect to negative externalities and the policies to mitigate them. In the scenario that we're getting ready to talk about, we have a pollution problem that the government wishes to reduce, and it is complicated by the fact that there are multiple emitters. This is, of course, a problem in the real world where the nature of pollution is greatly complicated by the fact that there are an innumerable number of polluters out there. And so one of the big things that policy will often need to be cognizant of is that if we're trying to reduce pollution sort of writ large, or a particular type of pollution, like say, sulfur dioxide or carbon dioxide, we need to have a really good understanding of the fact that there are multiple emitters and there are potentially emitters across industries, so on and so forth. We're going to keep things a little simple in this particular scenario. We're going to have just two polluters, and that alone creates some complexities, but also offers us to dig a little bit deeper into this conversation about cost-effective environmental policy. Okay, so in this particular scenario, what we have is a policy goal to take a situation in which there are currently 50 units of pollution being emitted, and we want to bring that level down to only 20 units. So we want to have 30 units of pollution abated. Okay, that's the policy goal. So first off, let's see how we arrived at this particular policy goal, because as we're going to see in a moment, that particular goal, 30 unit reduction, isn't just randomly selected. So we have two emitters, as I mentioned. Both of these emitters are production manufacturing plants that create pollution. What you see in front of you in equations 1 and 2 is the total abatement costs for each firm. Each firm would have to spend money to reduce their own pollution, and importantly, we can see that their costs are different from each other. We have what we call heterogeneous cost functions. For now, what we're going to do is we're going to establish what that optimal level of abatement is, and in order to do so, we need to have the total cost for abatement across both firms. So we just take the two individual abatement cost functions and we smush them together into a single abatement cost function. And we can see that the total abatement cost for society, if you want to think about it this way, so both firms, is 150 squared. Then we compute the marginal cost of abatement from that function, and we get a marginal cost of abatement of 300A. And again, A here is abatement, so it is pollution reduction. In the individual firm cost curves, you should see, of course, that the only cost the firm faces is how much they abate themselves. So the cost function for firm 1 only covers abatement from firm 1, and the same is true of firm 2. Now, in order to establish what the optimal level of pollution is, or in this case, what the optimal level of pollution abatement is, we're going to rely upon the first equimarginal principle, which tells us that the optimal level of anything is found at the intersection of the marginal cost of that thing and the marginal benefit of that thing. Now, in the context of pollution, we usually frame this as being the marginal damage of pollution relative to the marginal benefit of pollution. Here, we're going to instead think about it as the marginal cost of abatement and the marginal benefit of abatement. But because the first equimarginal principle is not really an environmental econ idea, it's really a mathematical idea, it carries over into both scenarios. And in fact, you can think about pollution policy as being about finding the optimal level of pollution, which would then therefore give you an optimal level of abatement, or finding an optimal level of abatement, which would then in turn give you the optimal level of pollution that you desire. Here is the total abatement benefit that society faces from the reduction of this pollution, which we then use to compute the marginal abatement benefit function. And if you will recall from the first equimarginal principle, the optimal level of something is found when the marginal benefit is equal to the marginal cost. So we just take the marginal benefit curve and we set it equal to the marginal cost curve. And when we do that and we solve for A, we get that A star is equal to 30. As we said previously, the policy proposal was for both firms, across both firms, to have a total abatement of 30 units, and this is where that came from. So if we go back to the first slide, we said the policy goal was a 30-unit reduction in pollution. We actually got that by first computing the optimal level of abatement at, in this particular scenario, which was 30 units of abatement. So again, given the characteristics of marginal abatement cost and marginal abatement benefit, we have determined that the optimal abatement level is 30 units. Now, we know what the optimal level of abatement is, but now the question becomes, well, who abates what? We have two firms. They have heterogeneous cost functions, so it doesn't cost them the same to abate. So how much should they abate? Well, the easiest solution, perhaps, is a form of what we might refer to as command and control policy. So in class, we've discussed the notions of command and control policy. This is a situation where the government imposes a particular standard and then enforces that standard, usually through some sort of legal action. So we can imagine that in this scenario, the government has established that they want to reduce pollution by 30 units, and that perhaps the most fair way to do this is just to have each firm reduce their pollution by 15 units each. Well, we can compute the cost of this by simply plugging in the abatement costs for each firm, and we can see that the total abatement cost is equal to $33,750. Now, this again is cognizant of the fact that the two individual firms have their own unique cost functions. So the kind of baseline cost to reduce pollution by 30 units is going to be $33,750. And we're going to compare this to another outcome in just a moment to see if we can do better, right? So we have established what the optimal level of abatement is. It's 30 units. If we simply have each firm split that optimal abatement across them, the resulting cost is $33,750. So the question is, can we do better? And the answer, of course, is yes. So we're going to look to what we refer to as the second equimarginal principle. The second equimarginal principle goes further than the first equimarginal principle. The first equimarginal principle establishes for us the optimal level at sort of the 30,000 foot view. But in this particular scenario, because we have multiple firms, we know what we want the total abatement to be across all the firms, but we don't necessarily know what each firm should abate. But we can answer that question. So here, once again, we have the total abatement cost functions. We're going to use these to compute marginal abatement costs for the two firms. So we can see marginal abatement cost for firm one is 200 A1, and the marginal abatement cost for firm two is 100 A2. Now, the second equimarginal principle tells us that the most cost-effective distribution of any activity across multiple entities is going to be found by setting the marginal cost across the multiple entities equal, meaning that the cost-effective level of abatement for each firm is going to be found where the marginal abatement cost for each firm is equalized. Well, this gives us a very simple mathematical technique for us to find the cost-effective level of abatement. So let's do that. We set marginal abatement cost 1 equal to marginal abatement cost 2. Okay, again, we got those functions here, 200A1, 100A2. So we simply set those equal to each other, 200A1, 100A2. We do a little bit of math here. And here I've solved for A2. You could leave it and solve it for A1. It really doesn't matter. I think the math is a little bit easier here by solving for A2, but only marginally so. So we arrive at equation 9 here, which says that A2 is equal to 2A1. Now, again, we have established that the second equimarginal principle is going to give us the most cost-effective guidance as it pertains to who should abate what, right? So the goal here is determining, okay, we know we want to abate 30 units in total. How many of those 30 units should firm 1 abate, and how many of those 30 units should firm 2 abate? Okay, so we first set marginal abatement costs equal to each other. And what this generates is an equation. And we're just going to call this equation 9. Doesn't really have a name. It's just equation 9 for our purposes. What we can do is we can use the policy goal equation because we know what the policy goal is. The policy goal is 30 units of abatement. So we can use that to create an equation. So abatement for firm 1 plus abatement for firm 2 is equal to 30, right? This is the policy goal. And then here again is that equation 9 where we found this by setting marginal abatement costs equal to each other. So what this does is it creates 2 equations and 2 unknowns. Okay? When you have 2 equations and 2 unknowns, it's very easy to solve for the solution. So here we just plug in A2 equals 2A1 into the policy goal equation. And when we do that, we get A1 plus 2A1 is equal to 30, right? Again, we're just taking this A2 is equal to 2A1 and we're just plugging it in here. So instead of A2 here, we're writing 2A1. We do some math here and we find that A1 star, which is the optimal level of abatement for firm 1, is equal to 10. Again, remember that in this scenario, the government just split up the abatement across the 2 firms, and that was 15 units each. We already see that that was incorrect in terms of cost effectiveness. In fact, the optimal abatement level for firm 1 is going to be 10 units. Then we can just take this value and we can plug it into either the policy goal equation or we can plug it in back into equation 9. It doesn't matter. Both of them will give us the same answer. And when we do that, we get that A2 star, that is the optimal level of abatement for firm 2, is equal to 20 units. So we can see that firm 1 should abate 10 units and firm 2 should abate 20 units. Again, this is significantly different than the solution where the government just split up the abatement across the 2 firms equally. And so what we can do is we can check to see if, in fact, this is indeed cost effective. So if we do that, if we have firm 1 abating 10 units and firm 2 abating 20 units, we see that there are significant cost savings, right? Just to remind you, the non-optimal baseline was $33,750. Now the optimal baseline is $30,000. So by using the second equimarginal principle, what we have done is we've saved ourselves money. We have come up with more cost-effective policy. So not only did we establish what the optimal level of abatement was generally, using the first equimarginal principle, we then use the second equimarginal principle to establish what the optimal level of abatement was for each individual firm. And again, you should notice that this is significantly cheaper than it was under the command and control without equalized abatement, right? So now the question sort of comes up, which is, okay, so in order for us to arrive at this cost-effective version of this problem, we need to know what the abatement costs are for each firm. We need to know what the benefit is to abatement, and then we need to have a policy goal, right? And we use the first 2, the costs and the benefit of abatement, to determine that particular policy goal. Now, beyond that, we then have to choose what policy mechanism that we're going to use. Again, the government could use what we call command and control policy, which is just mandating a particular level and then, enforcing that through some sort of legal process, or, punishing those who violate the particular rule. But of course, the problem with command and control policy is that it's very administratively burdensome. You need government bureaucrats who are guided by, the social optimum and not perhaps their own self-interest, which can be problematic. And so there's a lot of problems with command and control policy. And so the question in environmental economics is like, is there a better way? Right, just like we asked previously, is there a better way than having the government simply split up the abatement across the two firms? And the answer was yes. So now an additional question is there a better way to do it than, say, command and control? In other words, can we achieve the optimal solution, which again is for firm 1 to abate 10 units and firm 2 to abate 20 units? Can we get to that solution without the government requiring it? Right? Is it possible for us to get to that solution, not by the government mandating it, but instead relying upon what we refer to as market-based mechanisms? We have discussed one particular type of market-based mechanism, and that's the Pigovian tax. And the theoretical idea behind the government tax, the Pigovian tax, is that if we know what marginal damage is, we simply set the Pigovian tax equal to marginal damage, and this will cause an internalization of the externality and pushes us closer towards social optimality. In this particular scenario, we haven't really said anything about the damage caused by the pollution. And so as a result, we don't necessarily know offhand what the Pigovian tax should be. Furthermore, if I were to just tell you that the marginal damage was a certain amount of money, and then therefore we should set the Pigovian tax equal to that, it would be a fairly uninteresting thing for us to explore. So what I want to do is I want to actually go through the economics of how the Pigovian tax would work. And then once we establish that, we'll talk about, the actual kind of establishment of Pigovian tax. Okay, so if you look at this graph in front of you, what I've done is I've charted the marginal abatement cost curves for the two firms. Again, we established previously that firm 1 has higher marginal abatement costs than firm 2 does. And so you can see that reflected in the graph. And then what I have there for you is the line, the tax line. In other words, that's the level the tax needs to be at in order for us to get to the optimal solution. And just as you recall, the optimal solution is for firm 1 to abate 10 units and firm 2 to abate 20 units. Okay, so how does the Pigovian tax work? Okay, so think about what the trade-off is for each firm. Okay, they either abate their pollution or they pollute and have to pay a tax. Okay, so in either scenario, they face a cost. Okay, if they abate their pollution, they have to pay to reduce it. If they pollute, they have to pay to pollute. So now what we have is a comparable on the margin decision. Okay, so for every additional unit that a firm is considering either abating or polluting, we should be able to look at what the values are to the firm at that particular level and make a rationally self-interested decision. So for example, if we look at firm 1, okay, so we're looking at this curve here. If you look at units of abatement prior to 10, you'll see that the tax is greater than the marginal abatement cost for firm 1, meaning that, say, for example, if the firm is currently not producing anything and is deciding whether they want to produce 1 unit, they have to ask themselves, is the tax I would pay on that equal to, less than, or greater than the marginal abatement cost I would incur if I abated that unit? So again, assuming they're abating 0, does it make sense for them to abate this first unit if this happens to be the tax? And the answer is yes, because the tax is significantly greater than the marginal abatement cost is at this additional unit, which means it would be cheaper for the firm to to abate and pay the marginal abatement cost and avoid paying the tax. Okay, we can see that's true for firm one up until the point where we see that we've achieved the optimal outcome, which is 10 units of abatement. So at that point, if the firm is asking themselves, do I want to abate any additional units of pollution? If they do that, then their marginal abatement cost is now greater than the tax, which doesn't make sense. So instead of paying to abate beyond 10 units, it in fact makes sense for the firm now to just pay the tax and to pollute. So here we can see that the optimal solution is achieved whenever the tax is set such that it intersects the marginal abatement cost curve at the level of optimal abatement. So in other words, all we have to do is find the value that gets to this particular solution. And the beauty of it is that it's the exact same outcome as we can see here in the graph that gets us to the solution for firm two, right? Now for firm two, they are willing to abate more than firm one because their abatement costs are lower, but the exact same logic holds. They will abate until the tax they have to pay on pollution is less than their marginal abatement costs. And at that point, they'll start polluting. So in other words, what I have shown you here in the graph is the optimal solution to this problem, yet we still don't actually know what the level of the tax should be. So let's figure that out. Well, if I know what I need marginal abatement costs to be in order to achieve these particular levels, then I know what the tax is. And I know what marginal abatement cost is at these points because all I have to do is take the abatement level, plug it in to my marginal abatement functions, and that will tell me what this amount is. So if I do that, that is to say, if I find at what level of marginal abatement cost I experience as firm one when I abate 10 units, I can see that that's $2,000. Well, when I check this for firm two and their abatement of 20 units, I also get $2,000. What this means is that if we set the tax equal to $2,000, then this will fully incentivize firm one to abate 10 units, no more, no less. And it will incentivize firm two to abate 20 units, no more, no less, right? So imagine that this line is at $2,000, okay? As firm one is deciding how much to abate, they see that they can abate, they see that it isn't until they go past 10 units of abatement that their marginal abatement cost is greater than $2,000, right? So they will stop abating at 10 units of abatement, and beyond, they will simply pay the $2,000 tax as opposed to the higher marginal abatement costs. And of course, for firm two, same thing happens, just happens a little bit later. Firm two is going to abate 20 units, and then beyond that abatement level, it makes more sense for them now to pollute and to pay the tax. So again, the way that the Pigovian tax works is it causes the firms to internalize the negative externality. And even if we don't know what marginal damage is, if we actually know what the optimal level of abatement is for the two firms, we can actually back out what the appropriate Pigovian tax would be. And here, the appropriate Pigovian tax is the one that equalizes the marginal abatement costs across the two firms at their optimal levels. And again, we see that that's $2,000. Okay, finally, we're going to introduce the concept of cap and trade. We have not really talked about cap and trade in class, but it is a potent and interesting form of environmental policy. The idea behind cap and trade is that the government establishes a cap, that is an amount of allowable pollution, and then they create permits for that cap. And in order for a firm to emit, to pollute, they need to be able to have a permit. So you need a permit in order to pollute. And so what the government does is they distribute pollution permits to firms, and then they allow firms to buy and sell pollution permits from each other. And the idea is that the natural differences in abatement costs across the two firms will also be reflected in those firms' willingness to buy and sell pollution permits. Okay, so the simplest example that we can cover is if the government simply gives an equal number of pollution permits to both firms. So in this scenario, they would give each firm 10 pollution permits. Because again, remember, the government wants to have total pollution emittance of only 20 units. So they're going to give 10 units of pollution permits each to each firm. And so if each firm simply uses those pollution permits and nothing else changes, we're going to get 10 units of pollution from firm one and 10 units of pollution from firm two. But as you probably are already realizing, that's not going to be the optimal solution. Okay. So we actually want to think about this in a similar way to the tax, except we're not going to think about it in terms of the tax. We're going to think about it in terms of the permit price. Okay, so you'll notice here, instead of this line being tax, this is referring to permit price. Okay, so in this particular scenario, we have given firm one 10 pollution permits. Okay. Now, it's important to remember what firm one was emitting prior to any policy. Firm one was emitting 25 units. Also, firm two was emitting 25 units. And so by polluting 10 units, this means that firm one would have to abate 15 units. Okay, so again, firm one is currently emitting 25 units of pollution. The government then says you can't emit that much anymore. So what we're going to do is we're going to give you pollution permits, and you're only going to be able to emit 10 units of pollution. This means that they must abate the other 15 units of pollution. So they emit 10 units of pollution, and then they have to abate the other 15 units. Okay, so we're looking here at the graph to the left. If we look at this scenario, the dot here represents the current level of abatement, assuming the firm does not buy or sell their permits. So they were given 10 permits. Let's assume they just use them. If they just use the pollution permits, then they're going to have to abate 15 units. But you'll remember that we already know that the optimal solution is for firm one to abate 10 units. And primarily we know this because it's where the marginal abatement costs were equalized across the two firms. So the first thing to notice is that without any buying and selling of these permits, we do not arrive at the optimal solution, right? The optimal solution is only going to be found when the firms actually engage in trading permits, right? It's what we call it, cap and trade. Okay, so again, firm one is currently abating 15 units. They're abating 15 units because they're only allowed to pollute 10 units. But what you'll notice is that their marginal abatement cost is higher than it should be in the context of the optimal solution, which means that the firm is paying more for abatement than what would be cost effective that we've already established. If we look over here to the right, you'll see it's the exact opposite. For firm two to abate 15 units, this is in fact below what the optimal level of abatement is. Because in that context, firm one is paying more for abatement than they would like to, and firm two is paying less for abatement than, in a sense, they would like to, then this gives us opportunity for trade. Specifically, firm one is going to want to buy permits from firm two, and firm two is going to be willing to sell those permits to firm one. Here's why. Okay, again, this all goes back to the differing cost structures across the two firms. Firm one has higher abatement costs than firm two, right? Which we've already established. In this scenario, because there is this discrepancy in cost of abatement, firm one has it in their best interest to buy pollution permits from firm two, and firm two has it in their best interest to sell pollution permits to firm one. And here's why. At their current level of abatement, firm one is paying this amount for their abatement level, right? Which we already know is greater than $2,000, right? We haven't put a value here, but we know that this line represents $2,000, right? Because it's the line that creates this optimal outcome. And we already established in this example that that line is at $2,000. Okay, so you can think about this permit price as being $2,000. Well, so at this current level of abatement, firm one is paying greater than $2,000 to abate. So they would much rather be simply polluting, and instead of abating this, polluting and just paying the permit price for it. And then for firm two, it's the exact opposite. Here, their abatement costs are below $2,000, which means they would be willing to sell to firm one pollution permits and at $2,000, and they will do so up until the point when we have achieved the optimal solution, because it's beyond this point where now the firm two is no longer willing to sell pollution permits, because beyond 20 units of abatement, we can see their abatement cost is greater than the permit price. So they have no incentive to sell more pollution permits to firm two, right? And the same scenario over here. Firm one will buy pollution permits until we've achieved the optimal solution, because any less abatement for firm one would in fact be at a lower abatement cost than what they could receive in terms of the pollution permit. And so basically the way this works out is that firm two will sell 5 pollution permits to firm one, and firm one will use those 5 pollution permits to reduce their abatement to 10 units, and firm two will increase their abatement level to 20 units. And again, what this boils down to is this on the margin decision. All right. If a firm could sell a pollution permit to another firm and instead abate, and they would make money on that transaction, they would be willing to sell pollution permits. On the other hand, if a firm could buy pollution permits instead of abating, and that would make financial sense to them, then they're going to buy pollution permits. So in this particular scenario, it makes financial sense for firm one to buy pollution permits. It makes financial sense for firm two to sell pollution permits. And so just like with the Pigovian tax example, we don't need the government to necessarily tell each firm what they should emit or what they should abate. In fact, what we're simply allowing for is the natural economics of the two firms having different abatement costs, and we're using that fact to allow the firms to engage in pollution permit trading. And the outcome is exactly what we saw under the second equimarginal principle, which we also saw under the Pigovian tax. So the Pigovian tax, as well as the cap and trade program, theoretically should enable us to achieve the cost-effective and optimal level of pollution, which is not only for the total level of abatement to be equal to 30 units, but that firm two will have abated 20 of those units, and firm one will have abated 10 of those units. It doesn't matter whether we use a Pigovian tax. It doesn't matter whether we use a cap and trade. Theoretically, the exact same outcome should arise. And the last sort of point, which is really interesting, is that the optimal Pigovian tax is going to be equal to the optimal pollution permit price. And again, this is simply out of the natural economics of each firm, again, looking out for their own rational self-interest, and us as policymakers using that rational self-interest to achieve the policy goals that we wish.